we again have the problem of the rope over the pulley. 6 gram mass on this side, 6 kilogram mass on this side, 5 kilograms on this. Previously we did this first assuming that the rope has no significant mass, then assuming the rope did have a significant mass per unit length. Now we're going to assume that the rope has some kind of a mass density, but the mass density is a function of position along the rope. The rope gets thicker as we go from one end to the other. So we're going to posit a rope density, lambda of, we'll call the distance from along the rope from the 6 kilogram mass, we'll call that distance x hat. And now we're going to say that the density as a function of x hat is half a kilogram per meter. We have that throughout the rope, but then we're adding 0.01 kilogram per meter squared times x hat. Okay, now thinking of the units, it's presumably if we express x in meters, then this quantity becomes 0.01 times whatever x is, and it'll be kilograms per meter. And that'll match up with the kilograms per meter that we have here. So we need the meter squared here because we're going to have a meter here, and we want to get kilograms per meter because this is density per unit length. Okay, mass per unit length. Now, if the 6 kilogram mass, what we want to do is we're going to release this thing again when the 6 kilogram mass is 1 meter below the pulley. We release it from rest, and we're going to let it fall to the floor. Again, the rope is 20 meters long. The pulley has negligible friction and negligible dimensions, so that we have 1 meter of rope here and 19 meters of rope here. And actually we can't just release it from rest here because between the rope and the 5 kilogram mass on this side, we've got more mass here than we have here. So if this is resting on the floor, that's where it's going to stay. We have to give the thing an initial velocity in order for it to reach the floor on this side. Okay, and at some point here, the mass on this side will become greater than the mass on this side. Because we only have 5 kilograms here, we have 6 here. At some point, you'll have more rope on this side. Well, you'll have, certainly at some point, you'll have more rope on this side than this. And certainly at that point, you're going to have more mass on this side because you've already got 6 kilograms and 5 kilograms. Now, at some previous point, the masses will match. Okay, but right now the predominance of mass is on this side. Okay, now, what we want to figure out is the mass of rope on the right and the mass of rope on the left as a function of the position of this 6 kilogram object. So the mass of rope on the right is going to be the integral from 0 to x, because if you got x length units of rope, if you've got length x of rope over this side, then the rope from the 6 kilogram up to the position x will obey this density equation, and that's going to be the integral from 0 to x of your density, and that's an easy integral to perform. And I didn't write out the details of the integration. You're integrating 0.05 kilograms per meter plus 0.01 kilogram per meter squared times x hat. With respect to x hat, you're going to get 0.05 kilograms per meter times x hat, 0.01 kilograms per meter squared times x hat squared over 2. When you then substitute the limits to find the change in the value of that antiderivative, you're going to end up with this. You can perform that integral yourself. It's very simple. So that's the mass on the right. Okay, the mass on the left, well, you integrate for the rest of the rope. You integrate from position x, which will be here, to position 20 meters. Same thing. And if you do the integration, I believe this is what you get, and here's your final result. And it's a straightforward integration, so do it yourself and verify whether I've done this correctly or not. The net force then is equal to what? It's equal to the mass on the right times, well, the negative of the mass on the right times the acceleration of gravity, because of course the weight of the rope plus the 6 kilograms on the right acts in the counterclockwise direction, which we'll take to be negative. And the mass on the left here will be multiplied by the acceleration of gravity, and that'd give you a positive force relative to the counterclockwise direction being positive, okay? So here's your net force then. You have negative 10 newtons. Now where does the negative 10 newtons come from? 60 newtons on the right, 50 newtons on the left, is a net of 10 newtons on the right. A weight on the right hand side here is going to give you a torque in what we regard as the negative direction, or force in the negative direction. We'll distinguish between force and torque soon. But that's the way it comes out. So you get a negative 10 newtons from the two masses, and that's the same as it was before. Plus the mass on the left times g minus the mass on the right times g for the reasons I just outlined. And then we integrate that, and that's going to be our change in kinetic energy. Now we ran out of time at the end of class. We weren't able to integrate this, but we can easily do that now. The integral, and that should be F net, of F net ds is the integral from 1 meter to 19 meters of what? Negative 10 newtons plus the mass on the left, which is 1 kilogram per meter. Now some of these things are going to go together. We have a negative 0.05 kilogram per meter squared times x, and a negative 0.01 kilogram per meter squared times x squared. And actually, maybe I did simplify the whole thing, so maybe I better write all this down. Okay, minus 0.05 kilograms per meter squared. If you want to skip, a couple of minutes of writing this stuff down, feel free if you know where we're going. But if you need to watch, here we go. Then plus 2 kilograms per meter minus 0.01 kilograms per meter squared times x squared over 2. Now this could be simplified. The 1 kilogram per meter and the 2 kilogram per meter would give us 3 kilograms per meter, so I'm going to go ahead and do that. And of course, dividing this by 2 gives us a 0.05 here. But there's more. Then we have to subtract, and that's all times using the approximation 10 meters per second squared for the acceleration of gravity. There's the mass, there's the acceleration of gravity. Then we do the mass on the right, which is 0.05 kilograms per meter times x plus 0.01 kilogram per meter squared times x squared over 2, again multiplied by 10 meters per second squared. It's all this with respect to x, with respect to x. We're done with the x hat. Now if we collect all this, we have the negative 10 newtons here. We're going to have minus 0.05 kilogram per meter squared times x, and I left the x off of that. And we have a negative 0.05 kilogram per meter squared times x here. Where did I write that? Okay, that's kilogram per meter squared. No, I'm sorry. Kilogram per meter. And this came from this term. Should be kilogram per meter because we have the 20. Okay. So my meter squared was wrong there. Things are messed up here. I'm going to stop here, fix it, and then I'll come back because my units don't look like they're all right.